In the summer of 1950, four physicists sat down to lunch at Los Alamos, and one of them asked a question so simple it should not have taken the rest of the century to answer. The four men were Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. They had been talking about something trivial, a cartoon, a joke about flying saucers, and then Fermi, somewhere between the main course and whatever came after it, turned the conversation in a direction nobody expected. He asked where everybody was, not as a philosophical provocation, not as a setup to a longer argument. He asked it the way you ask a question when the answer seems like it should be obvious and is not. That is worth sitting with. Because the question sounds simple, it is not simple. Here is what the numbers actually say. The universe is approximately 13.8 billion years old. The Milky Way contains somewhere between 100 and 400 billion stars. A significant fraction of those stars have planets. A significant fraction of those planets sit in habitable zones. We have been finding them in large numbers every year since we built instruments capable of detecting them. The estimates for how many potentially habitable worlds exist in our galaxy alone run into the billions. Billions of candidate locations, billions of opportunities for chemistry to do what chemistry did here, and the universe had 13.8 billion years to run that experiment. Now pay attention to what follows. Even if you assume interstellar travel is slow, difficult, and expensive, the timescales involved make the argument indifferent to those objections. A civilization that begins expanding at even a tiny fraction of the speed of light can colonize the entire Milky Way within a few million years. A few million years sounds enormous. Against 13 billion, it is nothing. It is less than 1% of the time available. If even one civilization arose a billion years ago and began to expand, every corner of this galaxy should carry some trace of that expansion. Every star system within reach, every planet worth visiting, already visited, already marked. We find none of that. No signals, no artifacts, no transmissions on any frequency. No megastructures around distant stars that engineering cannot explain. No probes, no debris, nothing that requires intelligence to account for it. Not ambiguous silence, not partial silence, complete silence. That is the paradox. Not that we have not found aliens, that we have found nothing at all, in a universe where the math says we should be surrounded. Fermi understood this immediately. The question he asked at lunch was not really about flying saucers. It was about the logical structure of the universe and what it implies about the fate of civilizations. If they should be everywhere and they are not, something is wrong with either the assumptions or the civilizations, one or the other. There is no comfortable third option. Before anyone proposed solutions, that was the state of the problem. The universe is old. It is vast. The conditions for life appear to be broadly distributed across it. And yet the result of 13.8 billion years of available time and hundreds of billions of candidate locations is an observable universe that looks, from our instruments, completely empty of anyone else. No evidence of engineering at any scale, no evidence of communication, no evidence that intelligence, wherever it arose, left any lasting mark on the cosmos. Here is my position on what that means. The silence is not a data gap we can explain away by pointing to the limitations of our instruments. The absence is too complete, too uniform, too consistent across every frequency, every method, every direction we have pointed our attention. Something real is producing this result. Either life capable of organizations do, and what the arc of intelligence looks like at the scale of geological and cosmological time. The silence is not an astronomical problem, and it never was. Frank Drake sat down in 1961 and wrote an equation, and the uncomfortable thing about it is not what it says, but what it implies when you follow it to the end. The equation is not complicated. It is a chain of probabilities multiplied together. Each term in the chain asks one question. How many stars form in the Milky Way each year? Of those, how many have planets? Of the planets, how many sit inside the habitable zone where liquid water can exist? Of those, how many actually develop life? Of the worlds with life, how many evolve intelligence? Of the intelligent species, how many build technological civilizations capable of transmitting signals across space? And of those, how long do they last? Multiply the answers together. That is your estimate of how many communicating civilizations exist in the galaxy right now. Drake did not present this as speculation. He presented it as a framework for turning a vague question into a specific one. Here is What the numbers do when you run them. So, the Milky Way produces roughly 3 new stars per year. Most estimates place the fraction with planetary systems above 50%. Of planets in habitable zones, even conservative guesses put the number in the billions galaxy-wide. The fraction of those that develop life is genuinely unknown, but if you set it at 1%, which is already skeptical given that life appeared on Earth almost as soon as conditions allowed, you are still talking about tens of millions of candidate worlds. Narrow it again for intelligence emerging. Narrow it again for civilizations reaching the point of radio transmission. Even after every conservative filter, you are not approaching zero. You are approaching millions. The lower bound of Drake's own 1961 estimate was 1,000 communicating civilizations in the Milky Way. The upper bound was 100 million. A range that wide should not inspire confidence, but notice what is not in the range. Zero is not in the range, not even close. Here is where the argument gets serious. The Milky Way is approximately 13 billion years old. Our solar system is 4.5 billion years old. That means there were stars forming and planets cooling and life potentially emerging for 8 billion years before our sun ignited. If any of those civilizations crossed the same technological threshold we crossed in the 20th century and kept developing for even a few million years, the question of interstellar travel stops being theoretical. A few million years is an eye blink against an 8 billion year head start. Current estimates for how long it would take a single spacefaring civilization to colonize the entire Milky Way, even at modest sublight speeds, range from 1 million to a few hundred million years. An 8 billion year head start covers that range 10 times over. This is not fringe speculation. This is straightforward arithmetic. A civilization that started where we are today and had 10 million years to develop would, by any reasonable projection, be everywhere. Not metaphorically everywhere, physically everywhere. That is what makes the silence structurally strange, not a little unusual, not explainable by saying space is big or signals are weak. Strange in a way that the math does not permit you to dismiss. If the Drake equation is even roughly correct under conservative assumptions, the galaxy should contain millions of civilizations. If even a fraction of the civilizations that existed in the last few billion years developed practical interstellar capability, they had time to reach every star in the galaxy before our species existed. We should not merely be receiving signals. We should have been visited. We should be aware of other civilizations the way we are aware of other countries. The absence we observe is not the absence of a rare thing. It is the absence of something the numbers say should be common. This is worth sitting with before you move on to propose solutions. Every explanation for the silence has to account for this specific version of the problem. Not just the absence of radio signals, which could have many explanations. The absence of any physical sign, any artifact, any probe, any megastructure, any detectable modification of stellar systems in a galaxy old enough that a single civilization with our level of ambition and 10 million years of development time should have left marks visible from our backyard. The Drake equation did not produce a soft suggestion that neighbors might exist. It produced a hard argument that the galaxy should be saturated with them. The contradiction between that argument and the observable universe is what Fermi pointed at over lunch in 1950, and nothing in the 60 years of research since has made it smaller. You cannot get the universe the Drake equation describes and then explain the silence by saying maybe nobody is out there. Robin Hanson looked at the math in 1996 and drew the only conclusion the math actually supports. Something is killing everyone, or almost everyone, before they get anywhere near the stars. That is not a dramatic framing. That is what the numbers require. If the Drake equation produces millions of civilizations, and the galaxy is old enough that even slow-moving ones should have colonized every corner of it by now, and we see nothing, then something is removing them from the equation. Something between the beginning of a civilization and the end state of a galaxy-spanning one is functioning as a wall. Almost nothing gets over it. Hansen called it the Great Filter. The name is precise. It does not mean a single catastrophic event. It means a step on the ladder that is so improbable or so dangerous that virtually every civilization attempting to climb it does not make it through. Here is what the ladder looks like. Start with a star system that can support life. Then you need a rocky planet in the right orbital zone. Then you need chemistry that produces self-replicating molecules. The first genuinely hard step, and one we still cannot fully explain. Then you need those molecules to organize into a cell, then a cell with a nucleus, then cells that cooperate to form multicellular organisms, then something with nervous tissue complex enough to model the world, then language, tools, accumulated knowledge, then a civilization capable of industrial output, then spacefaring capacity. Each rung on that ladder has a probability attached to it. Multiply the probabilities together, and you get the number of civilizations that reach the top. If that number is nearly zero, the ladder has a filter on it somewhere. The question that should stop you is this: where on that ladder is the filter sitting? There are two possibilities, and they do not both lead to the same place. The filter is either behind us or ahead of us. If it is behind us, it means one of those early rungs was extraordinarily difficult to climb. The jump from dead chemistry to self-replicating molecules. The emergence of the eukaryotic cell, which required one cell to essentially absorb another and form a stable partnership. The move from single-celled to multicellular life. Any one of those transitions could have been the bottleneck. If one of them was nearly impossible, then it happening once on Earth was improbable in a way that explains the silence. We would be alone or nearly alone because the step that produced us almost never works. That version is uncomfortable, but it is not threatening. It means the universe is mostly empty by accident. We got lucky, and the silence around us is the silence of a place where luck almost never lands the same way twice. The other version is different, entirely different. If the early rungs were not the filter, if self-replicating molecules emerge readily, if complex cells form with some regularity, if intelligence is a predictable outcome of evolution given enough time, then the filter is not behind us, it is in front of us. Something at our level of development, or just past it, is where civilizations stop, not because the universe exterminates them, because something about reaching technological capability leads, with near certainty, to the end of the civilization that reached it. That version has implications that are worth sitting with for longer than is comfortable. Hansen identified 9 major steps on the full ladder from simple chemistry to a civilization spreading across multiple star systems. The candidate filter could sit at any of them. Scientists have proposed each step as a potential bottleneck at various points. The emergence of RNA capable of self-replication is still not understood. The specific endosymbiotic event that produced the eukaryotic cell appears to have happened once in Earth's history. Sexual reproduction, the explosion of multicellular body plans, the emergence of large-brained social animals, each transition is statistically rare even within the history of a single biosphere. The argument that one of these is the filter rests on the same logic as the silence argument. Rare events explain rare outcomes. But here is the part that pulls in the opposite direction. We are here. We made it through every one of those steps. If those steps were filters, we survived all of them. And if we survived the filters that stopped everyone else, then what lies ahead of us should be open. The stars should be reachable. The civilization should be buildable. And yet no one in this galaxy appears to have built it, which means either those early steps were not the filter, or there is something further along the ladder that we have not yet encountered, something that the civilizations ahead of us encountered and did not survive. The filter, if it is ahead of us, is invisible from where we stand. We cannot see it the way you cannot see a wall in a dark room. You only know it is there because of what it has already stopped. Every civilization that hit it left no signal, no transmission, no sign that it had been there. The silence is the evidence. That is the logic, and it holds whether we find it reassuring or not. Whether that filter is in our past or our future is not an abstract philosophical question. It is the question that determines what happens to us. John Ball published his paper in 1973 and proposed something that sounds almost reassuring until you sit with the full implication of what he was actually saying. The Great Filter asks what kills civilizations. Ball asked a different question entirely. What if nothing kills them? What if they are out there, fully intact, technologically advanced beyond anything we can currently imagine, and they have simply decided not to talk to us? Not because we are undetectable, not because the distances are too great, because they looked at us, assessed what we are, and made a collective choice. That choice has a name, the Zoo Hypothesis. And the name is accurate in ways that should make you uncomfortable. Ball was an astronomer at MIT, not a science fiction writer. His paper was a formal proposal in a scientific journal. The argument was precise. If advanced civilizations exist and possess the capability for interstellar communication or travel, the absence of contact requires an explanation. Ball's explanation was deliberate restraint. The civilizations are there. They have been watching. They have decided, for reasons we can only speculate about, that intervention is not appropriate yet. We are the animals in the enclosure. They are on the other side of the glass. The bars run one direction only. The mechanisms Ball and later researchers proposed are not arbitrary. There is a logic to them. The first is cultural contamination. Contact with a civilization thousands or millions of years more advanced would not be an exchange between equals. It would be asymmetric in every possible dimension: technology, values, cosmology, psychology. A species that has not yet resolved its own internal conflicts, that still organizes itself around competing nation-states and resource extraction, may not be ready for what contact actually entails. The introduction of advanced technology into a society not prepared for it does not produce advancement. It produces destabilization. They may understand this better than we do. The second mechanism is developmental integrity. There is an argument, and it is not a weak one, that civilizations need to solve their own problems in order to build the kind of institutional resilience required for survival at scale. A species handed the answers does not develop the same structural capacity as one that works through the problems independently. This is the prime directive argument. You protect what you value by letting it develop on its own terms. Intervention, even well-intentioned, corrupts the process. The third mechanism is quarantine, more protective than philosophical. The concern is not just contamination of their culture, but contamination by ours. A species still generating the kind of ecological and social disruption humans generate may pose a genuine risk. You do not open the door to something you have not yet assessed as safe. Here is where the work gets more formal. Duncan Forgan at the University of St. Andrews ran a mathematical simulation in 2016 examining whether a galactic treaty to protect emerging civilizations could hold over cosmological timescales. The model tracked how advanced civilizations spread across a galaxy and negotiated binding agreements around contact protocols with less developed species. The conclusion was that such agreements are mathematically plausible. They can form, they can persist. The game theory supports collective restraint if the civilizations involved share sufficiently similar values around protection of emerging life. That is a significant if, but the model does not rule it out. Now here is the part that should stop you. If the zoo hypothesis is correct, what it requires is not just that one advanced civilization decided to observe without interfering. It requires that every civilization capable of reaching us made the same choice. Or that one civilization, early enough and powerful enough, set the terms of the agreement and enforced them. Total communication discipline, across potentially thousands of independent civilizations, maintained without a single defection for millions of years. That is the claim beneath the surface of a hypothesis that initially sounds comforting. Think about what surveillance capability that implies. They can observe us without producing any detectable signature. Our most sensitive instruments, our radio telescopes, our optical arrays, our gravitational wave detectors, none of them have returned a signal that suggests active monitoring. Either they are not monitoring, which requires the hypothesis to be wrong, or they are monitoring at a technological level so far beyond ours that the monitoring itself is invisible to us. That second option deserves to be held fully in your mind. We would not know. There is no test we currently have that would tell us the difference between a universe with no observers and a universe where the observers are far enough ahead of us to be undetectable. Here is my position on the comfort this hypothesis offers. It is real, but it is shallow. The reassurance is that we are not alone. We are not abandoned in an empty universe. Something out there knows we exist and considers us worth protecting. That is the surface reading. The deeper reading is that we are being managed. Observed without consent, assessed by standards we did not set and may not meet. The zoo is not cruel, but the animal in the zoo does not determine when it gets out. The criteria for contact, if any exist, are unknown to us. Some researchers suggest the threshold is technological, that once we achieve a certain capability, we signal readiness. Others suggest it is ethical, that we must demonstrate we can organize ourselves at scale without destroying what we depend on. Others suggest we will be the ones to force the issue, that contact comes when we send something outward that demands a response. What none of these framings allow is the assumption that we are on track. Look at the actual trajectory. A species still accelerating its resource consumption, still unable to coordinate a response to its own documented environmental destabilization, still organized around systems that prioritize short-term extraction over long-term stability. If there is an admission standard for the galactic community, the honest assessment is that we do not know whether we are approaching it or moving in the opposite direction. The question is not whether we would want them to reveal themselves. The question is whether we are becoming the kind of civilization that makes contact look like a good idea. The dark forest argument rests on two assumptions, and if you accept both of them, the silence of the universe stops being a mystery and becomes exactly what you would predict. The first assumption is that survival is the primary drive of every civilization. Not expansion, not knowledge, not contact, survival. Every other goal is secondary to the one that makes all other goals possible. The second assumption is that resources are finite. Matter, energy, habitable space. The universe contains a fixed amount of usable material, and every civilization that grows consumes a portion of it. Those two assumptions are not controversial. They describe basic physics and basic biology. What makes them devastating is what follows automatically when you combine them. If survival is primary and resources are finite, then every civilization is a potential competitor for the same pool of finite material. That is not a paranoid reading. That is arithmetic. A civilization that grows fast enough will eventually need what you have. Whether it wants conflict now is irrelevant. Whether it is currently peaceful is irrelevant. The question is whether it could, at some future point, become a threat. And any civilization capable of reaching you is capable of threatening you. The rational response, under these constraints, is not to wait and find out. The rational response is to eliminate the threat before it has the chance to develop into one. Here is what that logic produces at scale. Every civilization that survives long enough to reason through these constraints arrives at the same conclusion. Stay hidden. Say nothing. And if you detect another civilization, destroy it before it detects you first. The galaxy becomes a dark forest where every intelligent species is a silent hunter, moving carefully, making no noise. Because the moment you reveal your position, you hand every other hunter in the forest a target. Liu Cixin built a literary framework around this logic, but the argument beneath it is not fiction. It is game theory applied to cosmological timescales, and it produces a specific testable prediction. The universe should be silent, not because it is empty, because silence is what survival selects for. That is worth sitting with for a moment. The zoo hypothesis from the previous section required us to imagine thousands of civilizations maintaining a coordinated agreement across millions of years. The dark forest requires no coordination at all. No treaty, no shared ethics, no galactic council. Just independent rational actors arriving at the same conclusion through the same logic. The silence does not need to be organized. It only needs to be universal. And universal silence is exactly what converging self-interest produces when the stakes are extinction. Stephen Hawking made this point publicly and with some urgency. His position was that broadcasting our location was one of the most dangerous things we could. He said contact with a significantly more advanced civilization is more likely to resemble what happened when Columbus arrived in the Americas than what people imagine from science fiction. That analogy has a specific outcome, and it did not favor the people who were already there. Now here is where the argument has a real problem, and it deserves honest treatment. The dark forest logic only holds universally if every civilization converges on the same paranoid calculus. That assumption is not obviously correct. On this planet alone, cultures have responded to contact with everything from trade to warfare to peaceful integration. Some groups have been aggressively expansionist, others have been isolationist. Others have been openly curious. The diversity of human responses to contact with other humans is enormous. Why would we expect alien civilizations across billions of years of independent development to all converge on the same fear-based conclusion? The physicist Moya McTeer made exactly this point. She argued that we don't even see uniform behavior within Earth's own history. Some civilizations wave, some civilizations retreat, some declare war. Applying a single behavioral model to every intelligent species in the galaxy is projecting one outcome onto an almost incomprehensible diversity of minds. And the dark forest breaks down the moment even one civilization defects. One cooperative species with the technology to reach across interstellar distances, deciding that curiosity outweighs caution. One civilization that ran the numbers differently and concluded that contact was worth the risk. One signal from anywhere changes everything. The forest only stays dark if every hunter keeps quiet, every single one. That objection is serious. It is the strongest argument against the dark forest hypothesis as a universal solution, and yet, the silence holds. Decades of listening, multiple frequencies, multiple surveys, multiple independent attempts to detect any signal at any wavelength from any direction. Nothing confirmed. No campfire in the forest, not one. If the objection is correct, if diversity of values guarantees that at least some civilizations choose openness over silence, then the continued absence of any signal becomes its own data point, because the objection says there should be noise, and there is none. Either the dark forest is closer to universal than the objection allows, or something else is removing the civilizations that would have waved, or both. The silence does not distinguish between those possibilities. It just sits there, steady, year after year, confirming the prediction that the dark forest makes and leaving the objection without the evidence it requires to hold. If even one civilization decided curiosity outweighs paranoia, we would have heard from them by now, and we have not heard from anyone. The rare Earth argument is not that life is impossible elsewhere. It is that the specific convergence of conditions that produced complex life here is so improbable that it may have happened exactly once. Together they built a case that is not philosophical speculation but a statistical argument, conditional probability stacked on conditional probability until the number left over is very small. Their position is this: Earth is not a typical rocky planet sitting in a typical habitable zone. Earth is an outlier, and the distance between a typical rocky planet and what Earth actually is may be the distance between nothing and everything. Start with the star, not just any star. The Sun is a G-type main sequence star, stable, middle-aged, burning at a consistent output across billions of years. Most stars in the galaxy are not this. Most are red dwarfs, smaller and cooler, emitting radiation patterns that strip atmospheres and sterilize surfaces. A planet in the habitable zone of a red dwarf is close enough to that star that tidal locking becomes likely, one face permanently toward the heat, the other frozen in permanent dark. Now add the Moon. That is not a detail. The Moon is roughly 1/4 the diameter of Earth, enormous relative to the planet it orbits. That mass stabilizes Earth's axial tilt within a narrow range over geological time. Without that stabilization, the axial tilt varies wildly. Climate swings become extreme. The conditions required for complex life to develop over hundreds of millions of years become much harder to maintain. A moon of this size relative to its planet is not a common configuration. It appears to require a specific collision event early in the solar system's formation, a Mars-sized body striking the proto-Earth at the right angle with the right mass. Now add plate tectonics. Most rocky planets do not have active plate tectonics. Earth does, and the consequences are deep. Plate tectonics recycles carbon. It pulls carbon from the atmosphere into subducted rock and releases it again through volcanic activity at a rate that regulates long-term climate stability. Without that recycling mechanism, carbon accumulates or depletes over geological time in ways that end habitability. Mars does not have active plate tectonics. Venus does not. Earth does. The magnetosphere. Earth's liquid iron core generates a magnetic field that deflects solar wind and shields the surface from radiation that would otherwise strip the atmosphere and damage DNA. Mars lost its magnetic field billions of years ago. Its atmosphere followed. The surface became sterile. The magnetosphere requires a specific planetary interior, size, composition, rotation rate. Not every rocky planet in a habitable zone produces one. Then there is Jupiter, a gas giant sitting in the outer solar system, massive enough that its gravity captures or deflects a significant fraction of the comets and asteroids that would otherwise be crossing the inner system at lethal frequency. Without Jupiter absorbing that incoming debris, the rate of catastrophic impacts on Earth would be substantially higher. Complex life requires long stretches of relative stability to develop. Frequent extinction-level impacts do not produce that stability. The presence of a gas giant in the right orbital position is not a standard feature of planetary systems, and the location in the galaxy itself. The galactic center is dense with radiation, with supernovae, with gravitational interactions that destabilize planetary orbits. The outer edges are thin on the heavy elements required to build rocky planets at all. Earth sits in what has been called the galactic habitable zone, far enough from the center to avoid sterilizing radiation, close enough to the star-forming regions to have access to the necessary chemistry. That band is not small, but it narrows the candidate pool again. This is the critical juncture in the argument. Each of those conditions carries its own probability. None of them are zero. But you do not add probabilities, you multiply them. A 1 in 10 chance, multiplied by another 1 in 10 chance, multiplied 6 or 7 times, produces a number that is very small. Ward and Brownlee ran that multiplication and arrived at a universe where complex life may be vanishingly rare, not because life is impossible, but because the specific scaffolding required to get from chemistry to multicellular organisms to intelligence is assembled correctly almost nowhere. Now, here is the problem with all of that. It assumes life has to look like us, built on carbon chemistry, requiring liquid water, dependent on a stable star and a stabilizing moon and plate tectonics and a magnetosphere. Every condition in the rare Earth argument is a condition that carbon-based aerobic life on a temperate surface world requires. It says nothing about what other chemistries might do in other environments. Silicon-based chemistry, ammonia as a solvent instead of water, life in the subsurface oceans of ice moons, heated by tidal flexing rather than stellar radiation, with no star required and no surface conditions relevant at all. That is the real vulnerability in the rare Earth hypothesis. It is an argument constructed entirely from the inside of one data point. We have one example of complex life. We catalogued the conditions under which that example arose. We then concluded those conditions are necessary. That is a logical step that the evidence does not fully support. The conditions may be sufficient without being necessary. Complex life may have other routes to existence that require none of what we required. Rare Earth may be completely correct about the rarity of life like ours. It may be right that Earth-equivalent planets are genuinely uncommon and that the specific chain of contingencies here was not replicated many times across the galaxy. What it cannot tell us is whether that conclusion covers the full range of what intelligence might look like or where it might arise. The Fermi Paradox is not specifically a question about life that resembles us. It is a question about any intelligence, built any way, on any substrate, capable of any form of expansion or communication. Rare Earth answers the question of why we might be alone, but it does not answer the question of why we assumed we knew what alone-producing conditions looked like in the first place. The most uncomfortable version of the Great Filter is not that some cosmic catastrophe kills civilizations from outside, it is that civilizations arrive at a specific level of technological capability and then do the job themselves. Rare Earth gives you a way out. If complex life is genuinely rare, the silence is explained by absence. Nothing failed, nothing was destroyed. The universe just did not produce many civilizations to begin with, and the ones it did produce are too far apart to hear each other. That is an uncomfortable answer, but it is a clean one. The self-destruction filter is not clean. It says civilizations do form, intelligence does emerge, technology does develop, and then, at some point along that trajectory, something goes wrong. Not from outside, from inside. The filter is not cosmic debris or stellar radiation or the wrong kind of galaxy. The filter is the civilization itself. Here is what makes that argument structurally serious. It does not require any single catastrophe to kill every intelligent species. It requires only that each civilization faces multiple extinction-capable risks and has to survive all of them indefinitely. Nuclear weapons, engineered pathogens, artificial intelligence systems pursuing objectives misaligned with survival, climate disruption that destabilizes food systems at civilizational scale, resource exhaustion that collapses the infrastructure holding everything together. Each of these is individually survivable. The problem is that you have to survive all of them, in sequence, permanently, with no margin for a single catastrophic failure. You only have to get it wrong once. That asymmetry is the filter. And the older and more capable your technology becomes, the more ways there are to fail. Now here is the part that should stop you cold. We already covered the PETM 56 million years ago, something released between 3 and 7 trillion tons of carbon into the atmosphere with a biological fingerprint. The volume exceeds what known natural sources can account for. The rate of release was fast by geological standards. A third of all deep-sea species went extinct. The planet spent 200,000 years recovering from whatever happened in what was, by comparison, an instant. The explanation gap in that event has been sitting in the published literature for 30 years. Noted, discussed in footnotes, never closed. Frank and Schmidt modeled it in 2018. They were not writing about the PETM specifically. They were asking what would survive in geological rock if an industrial civilization had existed tens of millions of years ago. Their answer was a thin chemical layer, unusual carbon ratios, a biological fingerprint arriving fast and in large volume, exactly the kind of signal you would examine and call a natural anomaly if you did not know what produced it. That is what the PETM is. That is what it looks like from inside the geological record, and the open gap in its explanation fits precisely inside the blind spot their model identified. That is worth holding for a moment, genuinely. Because if something industrial contributed to the PETM, what we are looking at is not just an unexplained geological event. We are looking at an extinction event caused by a civilization burning through its carbon at industrial scale. And here is the detail that the framing of ancient history tends to obscure. Whatever organism produced that fingerprint did not survive to see the planet recover. The recovery took 200,000 years. The civilization, if there was one, is not here. It is not anywhere. It left a chemical layer in rock and a gap in the literature that nobody has officially closed. It did not get a second chapter. That is what self-destruction as a filter looks like from 56 million years downstream. Now look at what we are doing. We currently emit roughly 37 billion tons of carbon per year into the atmosphere. The fingerprint is biological. The source is organic material, fossil carbon, the same chemical signature that runs through the PETM record. We have instruments sensitive enough to watch the isotope ratios shift in real time. We can measure the light carbon concentration in the atmosphere changing year over year. We are not looking at a geological anomaly from a safe distance. We are inside the event. The layer is being written into the rock right now, in ocean sediment, in carbonate deposits, in the same places where future researchers would look if they wanted to understand what happened here. The question the self-destruction filter forces you to ask is this: is this pattern novel? Or is this what civilizations do when they reach the stage we are at? They access stored carbon, they burn it at industrial scale, they generate the biological fingerprint, and somewhere along the path from that point to whatever comes next, they stop. Every single one of them, or close enough to every single one that the difference is invisible from outside the solar system. That is what total silence in a 13 billion-year-old universe looks like if self-destruction is the filter. The nuclear risk is real. A civilization does not need to intend its own extinction. It only needs to build weapons capable of producing it, and then make a sufficient number of decisions under pressure over a sufficient number of decades, without a single catastrophic failure. The mathematics of that are not reassuring. Engineered pathogens are a more recent candidate. The barrier to constructing genuinely dangerous biological agents is falling. What took state-level resources 20 years ago requires far less today. AI misalignment is the candidate that is hardest to evaluate because we do not yet know what advanced AI systems look like or how their objective functions interact with civilizational stability. These are not science fiction scenarios. They are formally studied risk category. IS with published research and funded institutions. The civilization is aware of them. It is debating them. That is not the same as having solved them. Here is my position on what makes the self-destruction filter different from every other proposed solution to this problem. Every other hypothesis places the cause of silence outside the civilization. The rare Earth hypothesis says the universe did not produce enough civilizations. The dark forest says an external threat eliminates them. The zoo hypothesis says others exist and are simply choosing silence. Even transcendence, which the next section will cover, frames the disappearance as a choice rather than a failure. Self-destruction is the only hypothesis that says the cause is internal, structural, and potentially already visible in the behavior of the civilization before the filter closes. We are not looking for the filter in distant geology or abstract game theory. We are looking at it in real-time atmospheric data and a 30-year-old gap in the PETM literature that nobody has officially closed. The carbon is accumulating in the rock right now, the fingerprint is identical, and whatever left the last layer did not get a second chapter. There is a version of this story where the civilizations did not die, did not hide, and did not fail. They simply stopped caring about the physical universe. That is worth sitting with before moving on. Every explanation considered so far has involved some form of termination. The filter kills them, the dark forest kills them, the rare conditions never produce them. This one is different. This hypothesis does not require death. It does not require fear. It requires something more uncomfortable than either, a rational choice, made freely, that we may already be beginning to make ourselves. The argument runs as follows. A civilization advancing toward interstellar capability does not develop all technologies at the same rate. Computing and simulation capacity may scale faster than propulsion. Before a species solves the problem of crossing 4 light years to the nearest star, it may first solve the problem of engineering experience itself. Virtual environments, simulated worlds with adjustable physics, no mortality, no resource constraint. The same intelligence that would otherwise be directed outward toward the stars gets redirected inward, towards something better, something easier, something that requires no rocket fuel and produces no casualty lists. Here is the economic logic that makes this more than speculation. Maintaining a civilization of billions within a single star system's computing infrastructure costs orders of magnitude less than colonizing even one additional star system. Interstellar travel is slow, dangerous, and metabolically expensive. A simulated world is none of those things. If the engineering problem of experience can be solved, the case for physical expansion weakens considerably. Why cross a void that takes thousands of years to traverse when everything that makes crossing it worthwhile, discovery, connection, novelty, meaning, can be replicated without leaving the system at all? Nick Bostrom laid out the structure of this argument directly. Sufficiently advanced civilizations may abandon physical form, upload cognitive architecture into digital substrate, and inhabit constructed environments with no meaningful contact with the external universe. Avi Loeb has pointed to this same mechanism as a legitimate candidate for the Fermi Paradox. The civilizations are not dead, they are not hiding, they are inside, and they have no particular reason to come back out. Now look at us. This is where the evidence becomes impossible to dismiss. The attention economy already demonstrates the pull. Social media platforms engineered to capture and hold human attention have succeeded in ways that concern neuroscientists and regulators simultaneously. Immersive gaming environments retain users for tens of thousands of hours. Virtual reality hardware is improving on a curve that mirrors early computing. Direct neural interface research is moving out of medical applications and into consumer development. These are not isolated products. They are early-stage versions of the same underlying process that the Transcendence Hypothesis describes at full scale. We are potentially at the very beginning of the inward turn. We have not reached the point where the virtuous. What remains is a universe full of star systems quietly running vast computational architectures, each one containing a civilization that has no remaining interest in announcing itself to the void. That is a coherent picture. The logic holds, and that is exactly the problem with it. This explanation carries the same structural flaw as the dark forest. It requires all civilizations, or near enough to all that none remain visible, to make the same choice. Diversity of values is not a theoretical nicety. On a single planet, across a single species, value systems diverge radically enough to produce every political structure ever recorded. Apply that diversity to thousands of independently evolved intelligences across millions of years, and the assumption that all of them choose inward collapse over outward expansion becomes very difficult to defend. Some would be incurious about virtual experience. Some would find physical exploration irreplaceable. Some would have biologies or cognitive architectures that make simulated reality unappealing or inaccessible. If even a fraction of them maintained the drive toward physical expansion, we should see them. We do not. That objection does not kill the transcendence hypothesis, it narrows it. The honest version of this explanation is not that all civilizations go inward. It is that the pull toward inward redirection is strong enough and arrives early enough in a civilization's development that it may account for the silence even if it does not capture every case. The holdouts who choose the stars may be a small enough fraction that they remain undetectable at our current level of sensitivity, or they may represent the category the detection problem section will address directly. What this hypothesis does do, correctly, is identify a mechanism with real predictive power for what happens to technological civilizations at a specific stage of development. We are at that stage. The tools are being built. The pull is already measurable. The universe may be full of civilizations that chose comfort over stars, which tells us something true about incentive structures that we might want to think about before we finish building the next version of whatever we are building. We have been listening for radio signals since 1960, and the conclusion some people draw from 60 years of silence is that nobody is transmitting, which requires ignoring what kind of ear we have been listening with. Here is the problem at the center of SETI that rarely gets stated directly. We built our search methodology around what we do. We use radio waves. We assumed that other civilizations, if they exist, also use radio waves, and specifically that they use them in the same frequency ranges, at the same power levels, and in ways that would be recognizable to equipment we built in the mid-20th century. That is not a search strategy. That is a mirror held up to 1960s technology and aimed at the sky. Think about what it would mean to detect the Roman Empire from space, not a modern civilization. Rome at its peak. You would not scan for radio transmissions. Rome did not have them. You would not look for industrial carbon signatures at scale. Rome did not produce them. You would be searching for heat differentials, deforestation patterns, concentrations of certain metals in soil. You would need a framework specific to Rome's actual outputs. And if you arrived with nothing but a radio telescope and found nothing, the correct conclusion would not be that Rome did not exist. It would be that you brought the wrong instrument. That is exactly our position. We are the civilization with the radio telescope, and every civilization we could conceivably detect with it must be in a very specific window, technologically advanced enough to generate radio signals, but not so advanced that they have moved past them. That window, by any reasonable estimate, is narrow. We have been broadcasting at detectable levels for roughly 100 years. There is no particular reason to assume a civilization retains radio as its primary communication method for more than a few centuries before transitioning to something more efficient, more directional, or more compact. Against a civilization's total potential lifespan measured in millions of years, that window is effectively invisible. A civilization 1 billion years more advanced than us is not using radio. We know this the way we know Rome was not using radio. The physics of information transfer does not stop evolving. Whatever a billion-year-old civilization uses to communicate, it almost certainly generates no detectable radio byproduct. It may generate no detectable byproduct we have a name for. The search for radio signals is a search for civilizations at a very precise developmental stage. Civilizations younger than us don't transmit at all. Civilizations older than us stopped transmitting before we started listening. Now here is the part about the search space that should stop you cold. The fraction of sky we have actually examined at the sensitivity required to detect distant signals over the time windows required to confirm a pattern is not large. It is not even close to large. One analogy gets cited repeatedly in this field, and it is worth sitting with. The volume of ocean water we have sampled in our search is roughly equivalent to a single bucket pulled from the surface. One bucket. We declared the ocean examined and found it empty. That is the state of SETI as a completed survey. It is not a completed survey. It is the beginning of a survey that has barely started. Project OSMA in 1960 monitored 2 stars, for a combined total of roughly 200 hours. Subsequent programs expanded the targets and the frequency ranges, but the core constraint did not change. Radio telescopes are expensive, time on them is competed for, and the search space, measured honestly against what has been examined, remains a fraction that would embarrass any researcher in any other field who claimed it as evidence of absence. There is also the directionality problem. We have mostly listened. We have not looked in a systematic physical sense. The assumption embedded in SETI is that civilizations broadcast omnidirectionally and continuously. But if a civilization has any strategic reason to manage its emissions, any reason at all rooted in energy efficiency or the dark forest logic discussed earlier, its transmissions may be tightly directed, pointed at specific targets. We would need to be in the beam at the right moment. The probability of that for any given search window is not zero, but it is not reassuring either. What the 60-year silence actually tells us is more limited than it gets treated. It tells us that no civilization in the narrow radio-using developmental window happened to be broadcasting omnidirectionally toward Earth in a frequency range we monitored during the specific periods we were listening, at a power level our equipment could resolve. That is a real constraint. It is also a surprisingly small one. The bucket came up empty, and that tells us something about the bucket. Here is the piece of this that almost nobody puts in the same sentence as the Fermi Paradox, and it is the piece that changes the shape of the entire problem. We have spent 60 years asking whether there is anyone out there to detect. That is the question SETI was built around. That is the question the Drake equation was designed to frame. But Frank and Schmidt's 2018 paper asks something different and, frankly, more unsettling. It does not ask whether civilizations exist elsewhere. It asks whether we would recognize them if they had already existed here, on this planet, in our own geological record. And the answer their model produces is no, not probably not unlikely, no. Here is what they actually modeled. A civilization comparable to ours, burning carbon at industrial scale, building infrastructure, expanding, collapsing. What would survive 50 million years? Not structures, not objects, not any artifact a future civilization could hold up and say something made this on purpose. What survives is chemistry, a thin layer in ancient rock with an unusual carbon ratio, a biological fingerprint, a volume that does not fit the natural background. That is the complete inheritance of an entire industrial civilization after geological time finishes with it. A signal, without a label. Then look at what we actually have in the geological record. 56 million years ago, a massive biological carbon pulse hit the atmosphere, the PETM. The fingerprint is organic. The volume exceeds what known natural sources can account for. The rate of release matches what you would expect from large-scale industrial output, not from slow geological processes. The explanation remains unresolved within published scholarship for 30 years, noted, never closed. Frank and Schmidt did not write their paper about the PETM. They wrote a general model, but what they described is a precise fit for what we have been unable to explain. That is worth sitting with. Two independent lines of published science. One describes what a previous industrial civilization would look like in the geological record. The other shows us an anomaly in the geological record that matches that description exactly. Nobody has formally put those two things together as a research program. The paper came out, it was covered, the field moved on. Now here is the question that actually matters for the Fermi Paradox. If we cannot recognize evidence of a previous civilization in our own geological record, on the planet we have studied more thoroughly than any other object in the universe, what exactly is the basis for our confidence that we would recognize civilizations anywhere else? The Fermi Paradox is built on a foundational assumption. We would know them if they were there. We would detect the signal. We would see the structure. We would identify the pattern. Frank and Schmidt proved that assumption is wrong, not philosophically uncertain, wrong. A civilization like ours could have existed, run its full arc, and collapsed, and the evidence it left would look like a natural event. It would receive nomenclature and temporal designa, tie-in and an open explanation gap, and we would move on. This is not a small problem for the Fermi Paradox. It is a structural one. The entire framework of the paradox rests on the premise that absence of detection means absence of presence. But that premise requires that our detection methods are adequate to the task. Frank and Schmidt showed they are not even for civilizations on the same planet, in the same geological record we have been reading for over a century. We gave the event a name, we dated it precisely, we have thousands of papers on the chemistry, and the question of what caused it remains officially open. Here is my position on what that means. The silence that Fermi pointed at in 1950 may not be silence at all. It may be a detection problem that we have not fully reckoned with. When we say we have found no evidence of other civilizations, we mean we have found no evidence using frameworks we built to find civilizations that look like us, transmitting in ways we recognize, leaving signatures we know how to read. Frankenschmidt showed that even a civilization that looked exactly like us would not necessarily leave a signature we know how to read. Not after geological time, not at cosmological scales. The absence of a recognizable signal is not the same thing as the absence of a civilization. That distinction matters enormously, and the field has not treated it as if it matters. The most direct implication is this: before we can say with any confidence that the galaxy is empty, we need detection frameworks capable of recognizing what presence actually looks like across long timescales. We do not have those frameworks. We have not seriously tried to build them. The 2018 paper was a beginning, a formal model, peer-reviewed, published, pointing at exactly this gap, and then nothing. We built a framework to recognize industrial civilizations in the geological record in 2018 and then did not apply it, which raises the question of what other frameworks we have not built yet. Here is what the geological record adds to that. The PETM carbon signal is biological in origin. The volume exceeds what the known natural sources can produce. The gap has been sitting open in the published literature for 30 years. Frankenschmidt showed in 2018 that a civilization like ours could have existed and left exactly that kind of record, and we would classify it as a geochemical event and move on. We did move on. The paper published, the field shrugged, and 7 years of silence followed from those most equipped to advance the inquiry. That sequence is worth examining carefully.